Hello, today we are going to be talking about 9.3, specifically combinations. And a combination is how do you order things? So let's imagine you went on a trip, a field trip. Let's say you're your band, and your band is going on to a field trip. You're playing in another city. Your marching band is going there, and there is 50 of you in this marching band, and you're all staying at a hotel. Here, let's say it's a hotel, and you want to figure out how many combinations can there be to match everyone up. And let's say there are 4 people per room in one room. And you're like, okay, well, how many combinations can I have of matching up all these 50 people? And there's only 4 people to one room. How many different ways can I pair these individual up into groups? So that number, the amount of how many times I can pair them up, and how many different combinations I have, that is my combination number, or my binomial combination number, because you can't repeat a human being again. They are their own individual. They can only be counted once. So that's how we're gonna go into going to answering that question. There's many ways to go about it, but first, normally, if you think about this, there are 50 people, right? So normally there's 50 people, and from those 50 people, you can only choose 4 in those rooms. And so if I put in 50 choose 4, we'd get about 230, 300,000 different combinations of groups of 4. That's a lot. But the question is, how do we get this mathematically? So there's one way you can get it is through the idea of our factorials. Here, if you think back to our factorials, we can write our combinations like this. This would be 50 or 4 or 50C4. Either way, they mean the same thing. In using factorials, we would have this being n and this being r. So this is n and this is my r. So here, using factorials, one way is n factorial over r factorial over minus n minus r factorial. So we can write that down now. So this gives me 50 factorial over 4 factorial over 50 minus 4 factorial is 46 factorial. 46 factorial. If I simplified this further, this gives me 47. If I took this out, this gives me 47 times 48 times 49 times 50 divided by 2 times 3 times 4. I can simplify. There is 2 times 3 and a 4 in 48. So 48 divided by 6 divided by 4. 2 times 3 times 4 goes into 48. That simplifies that to 2. So if I multiply 47 times 2 times 49 times 50, that gives me my number like so. But there's also another way about going this, and it actually comes from a French mathematician named Blaise Pascal, and he found or realized, we call it the Pascal triangle, that if we took all the potential combinations, so imagine if this is one person, there's only one combination. If this is two people, well, with those two people, there's only one combination and one combination. And then you just keep adding as we go down. We add them together. So 1 plus 1 makes 2, right? And then the exterior is always 1. 2 plus 1 is 3. And then we put in ones on the exterior. 3 plus 1 is 4. And 3 plus 3 is 6. And 4 and 1. And this can keep on going for infinity. So we'll just write down some of these here. So now if we wanted to say, oh, hey, I have 6 and I want to choose a combination of 5. Using the triangle, we would go down to the 6th row and not 5th, but 6 from the left. So 6 over. So this comes, we would count here. This is row 1, 2, 3, 4, 5, 6. I'd go 6 over. Well, 6 choose 5 would equal 1. And we can use the triangle for another one. Let's say we have 4 choose 2. Well, we go down 4. 1, 2, 3, 4. Count over not 2, but we count over 3. So we would go 1, 2, 3, and we get 6 using that triangle. Next, we're going to use this binomial choose method to expand a binomial to a certain power instead of having to FOIL out everything one piece at a time after another after another. What if we can use this? So let's say we have 5x minus 2y to the 5th power. It is onerous to do 5x minus 2y times 5x minus 2y all the way like 5 times. That's a lot. So there is a formula that we could use, the binomial theorem, that allows us to use this. So basically, since we take the power, we have 5 choose 0, and then we start with, I'm going to call this first one A, and I'm going to call the second one B, and so it would be A to the 5th, B to the 0, which is just 1, so then plus 5 choose 1, A to the 4th, B to the 1, plus 5 choose 2, A to the 3rd, B squared. As you can see, well, there's a little pattern developing. 5 choose 3, A 2, B 3, plus, I'll go down here, 5 choose 4, A 3, A, we're going down on A 1, B 4, and then plus 5 choose 5. There will no longer be a A, but now we have B to the 5th power. So let's fill this in further as we go. So 5 choose 0 is just 1. So we have the first term being 5x. So this is 5x to the 5th power. Second one, 5 choose 1 is a 5. So we got 5 times 5x to the 4th power times negative 2y plus 5 choose 2, which is 10 times 5x to the third power times negative 2y squared plus 5 choose 3, which is 10 again. And this is 5x squared and negative 2y cubed plus, then the next one is 5 times 5x times negative 2y to the fourth power, and then finally once again 1. So then we have negative 2y to the fifth power. So let's simplify this even further. 5 to the fifth power is 3, 1, 2, 5 plus 5 to the fourth times 5 times negative 2. We got, ooh, that's a negative number. So this is negative 6. Oh, I forgot my x. X to the fifth here. Negative 6, 2, 5, 0. My x needs to be to the fourth power. My y is to the 1 power. 10, 5 to the third power times what? Positive 4 times 4 times 10. That gives me positive 5,000. X to the third power, y to the second power. Now 5 squared, that's 25 times negative 8 times 10 will give me negative 2,000 x squared, y cubed, and then negative 2 to the fourth power, that's 16. 16 times 5 is 400 x, y to the fourth power, and then 2 to the fifth power, negative 2 to the fifth power is negative 32 y to the fifth. Fix that 5 here. And that is how we would do instead of foiling all that out, you would use your binomial theorem to figure out the expansion form of a particular binomial.